So welcome to the last lecture of this course. So what we're going to be doing, talking about radioactive half-lives and also nuclear clocks and dating, and we'll finish off with a bit of penetration of matter or radioactivity and shielding basically. So what we're going to do, let's talk half-life. So basically what happens with nuclear material is if we were to take a number of atoms, so say we have 64 atoms, we take it over time. After a certain amount of time with nuclear breakdown, we're going to end up with half the atoms. So let's say this is 1 year. After 1 year with this, we'd end up with 32 atoms. Because if you have an unstable nucleus like 235 or cobalt-60 or whatever, strontium-90, some of them are going to break down. And the trick is, if we have lots and lots and lots and lots and lots of atoms, this one might break down, and a bit later this one might break down, and this one might break down. We cannot tell individually which atom is going to break down, but over a period of time we can predict the behavior of the large sample. So if we've got 1 million atoms, we can say after a certain amount of time, well 64 atoms in this case, after a certain amount of time this year, we're going to have 32 left. And after another year, half of those are going to break down. So we'll end up with 16. And then after another year, so after 3 years, half of those would break down. So we'd end up with 8. And after another period, another year, we'd end up with 4. So every year, we're going to end up with half the number of atoms that we had the year before, or every half-life in this case. So this we call the half-life. And it's basically, the half-life is how long does it take for half the atoms to break down. And this is actually used nowadays, not just in nuclear, but in things like medicine. We talk about the half-life of the drug inside the body, and also over time, erosion, things like that. So half-life is a concept that's turned up in other places as well. So this is actually a very predictable form. In fact, it's basically nowadays, we call it an exponential decay. So let's actually work out a formula for this. So the number of atoms that we have after a time, number of atoms, is going to equal the original number, times half to the power of n, where n is number of half-lives. And so basically n is going to equal the time divided by the half-life time. Time for one half-life. So in that example I gave before, we said that the half-life time was 1 year. So every year we'd lose half our atoms. Now half-life times, can be vary quite considerably. So for U238, this is approximately 4.5 billion years. So after 4.5 billion years, you're going to lose half your 238 atoms. Something like hydrogen 8, and yes, somebody made hydrogen 8. They got a hydrogen atom and rammed 7 neutrons onto it. That's got a half-life of 10 to the negative 15 seconds, about there. So half-life times can vary dramatically. As a rule, the shorter the half-life time, then the more radioactive the substance will actually be. So just something to be aware of. So we'll just get rid of that. Now, this equation can also be written as NO over 2 to the power of N, so NT. And because, as I said, this type of curve before, we said that's an exponential decay, that can also be written as NT. And in this case, we're going to give it an exponential form. So the original number of atoms times E, and because it's a decay, it's going to have a negative exponent, so negative, whatever that is, times the time. Now this factor here, this is related to the half-life of one of these substances. So that's going to equal 0.693. This is a constant due to the fact that we're using E here, divided by the half-life time of one half-life. And for the time of one half-life, as I said, we can't actually predict when any individual atom decays, but we're going to actually, usually what we do is we take our sample and we can then start plotting points radioactive over time, and we can work out what this factor here is. So radioactivity actually does have a unit. It's like, you know, in physics we like to stick units on everything. So the unit for radioactivity time, units, we talk about decays per second. Decays per second. So how many, if we have a sample, how many decays do we get per second? Look, I'll go just get something. This is a piece of glassware I got given by a friend of mine, who I like very much. And you'll notice it's a green colour. And that green colour is caused by uranium ore. So back in the 1930s, before they started playing around with nuclear bomb, they thought uranium oxide gives a nice pretty green. So that has got uranium in it. So that is also radioactive. And I put a Geiger counter on that because, hey, yep, and it has several breakdowns per second, so it's not very dangerous at all. But you want to check. So 1 decay per second as I said, that does half a dozen, equals 1 becquerel. I better make sure I get the gentleman's name right, because Becquerel was a physicist who played around with radioactivity. So a becquerel is equal to 1 decay per second. And if, like this piece of green glassware, if it's only a few of those per second, usually nothing to worry about. It's about 6 times background radiation. Okay, so the next question is, another unit that we use is the Curie, named after Madame Curie, who played around with a lot. Now 1 Curie is equal to the radioactivity of 1 gram of radiation. Usually you can actually, if you have a radio and you put the antenna next to the 1 gram of radium, you can certainly hear it. Sounds like that, hence radioactivity. Now, so 1 Curie equals 3.7 times 10 to the 10 becquerels. And that is a lot of radiation. 1 Curie, if you're in it, is usually fatal. I remember that we did an experiment with 16 millicuries of radiation. And one of the things we had to do before we even were allowed to play with that much radiation was figure out how long we could actually stay in the room with that sample before we started taking damage. So anyway, as a rule, the more radioactive something is, then the shorter lived it is, of course, but the more radioactive it's going to be. So the shorter the half-life, the more radioactive something's going to be. Okay, so let's actually do an example. I'm just going to clear the screen. So what we have is radium. This is exercise 10.6. Radium has a half-life of 1,620 years. So that's actually quite radioactive for something that's naturally occurring. So how many grams, many atoms remain after 9,720 years? Okay, so first of all, we have to figure out how many atoms are in a sample. And so what we have to know is we have to know the atomic weight. So the atomic weight of radium is equal to 226. You just look that up somewhere, or usually you'll be given that in a test. You don't have to remember that, but we've got look up graphs or charts of all of that. So one mole of radium equals 226 grams. We also know 1 mole of anything equals 6.022 times 10 to the 23 atoms or molecules. That's Avogadro's number, in case you're interested. And I assume there's a long story on actually finding that number. So how many moles have we got? So number of moles is going to equal sample, so 1 gram over 226 grams per mole, which is equal to calculator time. 1 divided by 226 equals, I make that as 4.425 times 10 to the negative 3 moles. And then we multiply that by Avogadro's number, 10 to the 23 atoms per mole. So times 6.022 x positive 23. So I make that, in that sample, there is 2.665 times 10 to the 21 atoms. And that's going to be NO, because remember, we're going to be using the formula N time equals NO times half to the power of N. So this is NO, so we know NO. Now we have to work out N. N, remember, is equal to the time divided by the half-life time, which is equal to, the time we said was 9,720 years over 1,620 years per half-life equals, oh, let's get lazy, here's a calculator, 9,720 divided by 1,620 equals 6 half-lives. So that's 6 half-lives. So now we can actually stick this into this formula. So we've got N is equal to 2.665 times 10 to the 21 atoms times half to the power of 6 So let's try that. So 2.665 x 21 times 0.5 to the power of 6 equals, I make it 4.164 times 10 to the 19 atoms of radium, which somebody else has worked this out, is approximately equal to 0.016 grams of the sample. So that's how many you sample. And this is really cool, but it is of use. And yes, actually, we use this for doing things like working out dating. And I mean, probably the most famous of the whole lot is carbon dating, but we have other cycles we can use. So one of the ideas of radioactive clocks is if you take a sample, so I'm just going to clear this. So remember 4.164 times 10 to the 19 atoms, which is a lot. So if we take a, so let's talk, this is section, what's this, 10.5, radioactive clocks. What we mean by this is, can we tell how long something has been somewhere? And if we know what the half-life of something is, if we know it is pure to start with, we measure the amount of the stuff there was and compare it to the breakdown subject. The thing is, we know that there are very specific breakdown paths. Like the classic one is, take uranium-238. This is a classic path. So uranium, over a period of time, it will go through several steps. It'll throw out an alpha particle, it'll become thorium, and then it'll throw out stuff. It becomes a very specific isotope of lead. It becomes lead-206. And we know that the half-life time for this to go from uranium-238 to lead is going to be, what, 4.5 times 10 to the 9 years. So about 4.5 billion years to go from U-238 to 26. And it's going to do something like 8 alpha emissions down the way and occasional beta emission, all that type of stuff. So what we can do is, if we have a sample, and the sample doesn't actually have to be pure, if I measure the number of U-238 atoms, and I measure the number of 206 lead atoms, and if I compare this ratio, then I can actually tell how old that rock is. And this is what we actually use for dating some of the various oldest rocks on Earth. We have actually dated rocks back to like over 4 billion years ago on Earth. So let's try it. Exercise 10.7. We have a rock sample of has a U-238 206 lead ratio of 1:1. So that means for every uranium atom in there, there's one lead atom. How old is this rock? Well, we can tell from this that this is number of half-lives. It's going to equal 1 because it's because the amount of lead, so amount of uranium, equals half. And what we're talking about is the lifetime to do half. So that's one half-life we're talking about, because half of it has turned to lead. I mean, we can use that equation before and actually work this out. So we've said that one half-life equals 4.5 times 10 to the 9 we can, if you really want to, we can stick it into this equation. N time equals NO times half to the power of N, which is time over half-life. We want to find out T. So you can actually just rearrange that for T. And T over N equals half the half-life. Then you take the log of both sides. O log half T over half life. So, and it's power, so we can actually pull that out. Log N T over N equals, remember the exponent rule? Because it's a power, we can go T over half-life log half. And if you do, if you really want to, yeah, if you really want to, you stick all of that through your calculator, and equals 4.5 billion years. Or you could just go 1 half-life equals 4.5 billion years. Both ways work. So what we actually have, I'm going to clear all of that before. So one of the most common ones that we use is carbon dating. Carbon dating. And in fact, at the University of Waikato, we actually have a carbon dating laboratory where we can actually do carbon dating. And what we actually do is we measure the amount of carbon-14, because what we're actually measuring is the ratio of carbon-14 to carbon-12. Okay, because when plants, carbon-14 is created when basically nitrogen gets bombarded by cosmic rays in the upper atmosphere. And carbon-14 has a half-life of 14, half-life of 5,700 years. The amount of production is the same. So when a plant is alive, so if you have a tree and it's getting in fresh carbon all of the time, there's a ratio of 1 to 1.3 times 10 to the negative 12. So this is C12, C14. So there's a tiny amount of carbon-14, but remember carbon-14 is radioactive, so we can pick it up with a Geiger counter. So what happens is living plants pull this in, and it maintains this ratio, it maintains this ratio inside the plant. So when the plant dies, though, the amount of carbon-14 decreases. And what we can actually do is we can actually count the decays and say how old it is. Now, some people have saying about how you get you get things that show strange dates and things. But over many years, we've actually calibrated. Look, this makes the assumption the amount of carbon-14 production is constant. And it's not. But we have ways to compensate for that, because what we do is we look at tree rings. And we can then carbon date each tree ring, or work out how much tree ring. So we can actually work out, we can do tree ring back stuff thousands and thousands and thousands of years. So we can actually work out what the carbon-14 production was every year. So we can actually calibrate this very finely nowadays. But if you get a contaminated sample, it's still the same. So let's see. So if you're taking a fresh carbon-14, sorry, I'm just going to clear this. So fresh carbon-14 has a rate of approximately 16 decays, or 16 becquerel per gram of carbon-14. This is a sample with a sample This is not pure carbon-14, but if you take, what they do is they take a tree, they take a bit of the bird, they burn it so you get carbon, and they take the carbon, and if the carbon contains carbon-14 and it's absolutely fresh, it's going to have 16 becquerels per gram of carbon. Okay, so how old is, how old is a piece of wood that has an activity of 4 grams, 4 becquerel, or 4 breakdowns per gram. So the question is now at this point, remember n with time equals n O to the half to the n. So let's not even muck around with this too much. So what we actually can work out is 4 becquerels over 16 becquerels equals 1/4 the activity. And if we look at this equation, half to the power of 2 is equal to 1/4. So what it's going to be, this is that 4 becquerel per gram occurs after 2 half-lives. And remember, half-lives are constant. 2 times half-lives. Okay, so 1 half-life is equal to half-life times 2 equals 5,700 years times 2. What's that? 11,400 years. So that sample would be 11,400 years old. And so what we actually have about 20, 30 different radioactive clocks now. So we've got carbon which goes up to like 30, 50,000 years ago. And then we go into another one, and then we get to another one like strontium and things like that. And eventually we end up with our U238 to lead ratio. So we actually have all of these dating methods that cover over the time. The further out that we go, of course, the wider the bands become. So carbon-14 might give you time plus or minus 50 years. This will sort of give you a plus or minus a couple of million. But we actually have overlaps on all of them, so we can date continuously back. Oh, a few billion years, quite a few billion years now. So let's just do one last bit and we'll call it a day, and then you'll be done. So what about radiation of matter? So what happens is that you've got to watch out, because various types of things, radiation, are quite damaging. Alpha is going to be, yeah. But if you have gamma rays, for example, gamma rays, if we put some, gamma rays are really harmful because they can penetrate skin. Gamma rays penetrate skin and things, penetrate materials. And what that does is, if we have a sheet of lead here, for example, that's the classic one, some will get through and some will get stopped. And there's a certain amount of material here that will stop the rays getting through. So gamma rays, the question is, how much shielding do you need? How thick do you need? And this works exactly, if you do the same, a graph, number of photons or number of gamma rays penetrating, going through, versus distance, or thickness, then what we end up with is we end up with a graph that looks pretty much like the exactly like a half-life graph. So what we can say is the number of photons going through, or number of the gamma rays going through here is equal to the original number plus half to a thickness thing. So where N is equal to thickness of material that you're trying to penetrate over what we call the half distance. And the half distance is the thickness of the material that will stop half the gamma rays. So, I mean, one of the most common ones used in spacecraft and things is going to be aluminium. So let's see if, so the more energetic the photon is, or the gamma ray is, the half thickness. So if you've got a 1 mega electron volt gamma ray, it might get 4.2 centimeters, and 4.2 centimeters will stop half of it. If you get 5, then it'll take 9.1 centimeters to stop half of it. And this is going to act exactly the same way as, you know, the half-lives do. If you've got 10 mega electron volts, remember we can go up to 11.1 centimeters. It's going to stop. And it's one of those important considerations you have to look at when you're building shielding for things like nuclear reactors or experiments. How thick is the thickness? Like, I want a neutron activation facility, which is used for all sorts of things, needs quite a thick layer of stuff. The cancer machine up at the hospital has a particle accelerator that creates radiation. How thick do the concrete walls have to be to stop the radiation effectively so people walking past unharmed? And the answer is about 1 meter. So the walls up there around the radiation machine where for the cancer therapy are about 1 meter, 1.5 meters thick. And it's quite solid, I've actually seen. Quite impressive. Okay, so let's just do an example, and then we're going to call this a day and say the lectures are done. So exercise 10.9, a burst of 1000 gamma rays at 5 mega electron volts hits a 18.2 centimeter plate of aluminium. How many gamma rays pass? So let's draw a picture because I can. So here's our plate. We've got our gamma rays hitting. Some will go through, some will stop in the middle. Okay, so we're going to use that formula. N is equal to NO times half to the power of N, where N is the number of half distances, basically, or thicknesses or half distance. Okay, so what do we know? N is equal to, well, that's what we're going to find out. NO is equal to 1000. What's N? N is going to equal the thickness over the half distance. And we're going to do this in centimeters. I know that engineers are afraid of centimeters, but I'm also a physicist, so I'm not scared of centimeters. So the thickness we've said is 19.2 centimeters. Looking at that graph, that thing before, I said the half thickness of aluminium at 5 mega electron volts is 9.1 centimeters. So N is going to equal 2. And now we can just stick this into the equation. N, the capital N, the number of photons that get through, is going to be 1000 times half to the power of 2, which is equal to 1000 times a quarter. It's equal to 250 gamma rays. Okay, so we're going to let you loose on the world now. Good luck on your exam and your studies. And yeah, if you've got any questions, contact me. You got my emails. You got lots of contact information for me. So good luck in your exams, and hopefully we'll see you around the varsity.